All right, so we're back at it. Chapter 4. You are moving right along. Congratulations. And this is a fun chapter. You learn so much in this chapter. So we start off by telling a joke that I heard when I was a kid. Oh, my fan is giving me troubles here. Okay, so here's the joke. Ready? Now, if you've heard it, which I'm sure you've heard it, then we want you to think a little bit about the joke. What weighs more? A gram of gold or a gram of helium?
Gram of gold.
A gram of gold? That's what I said when I was young too. But the answer to the question is they weigh the same. You have a gram of each of them. A gram of gold or a gram of helium, right? Now, if I needed enough helium to actually have 1 gram worth of mass, I would need a huge volume of helium because helium has a very low mass, right? To get a gram of gold, I would just need a little tiny bit, right? But they would still have the same mass, which is 1 gram. So we would also hear other people say the joke, which weighs more? A gallon of gold or a gallon of helium? Now a gallon, what's that?
They're the same?
No, that's not right either because a gallon is a volume. A gallon is a fixed volume. So if I had a gallon of gold inside my milk container there, and then I had the same volume of helium, right? Well, the gold would have a much higher mass because the helium atoms in here wouldn't take up as much mass, right? Because they would be each atom of helium actually weighs less than an atom of gold. Okay? So, there's other things that are involved in this question and what the right answer is. But the one thing we want to recognize is that an atom of gold and an atom of helium have different masses. So, let's remind ourselves what number on this periodic table, looking at helium, here's helium, and here's gold. What number on here tells me the mass of the helium? What do you think? Which is the 2 or is it the 4?
4.
The 4. The 4 is the average mass of an atom of helium. How about an atom of gold? How much is the average mass of an atom of gold?
196.
Very good. So 196, that's almost 200, right? So it's almost 100 times or 50 times heavier than an atom of helium, right? So just because I have the same number of elements doesn't, in any given condition, it doesn't mean that those elements have the same masses as each other. All right? So, for now, we've never really talked about what units are on these numbers in the periodic table. For example, carbon, we know that the 6 is the number of protons, and the 12.011 we say is the average number of protons plus neutrons, and we call that its mass number, but we've never told anybody or talked about what the units are in terms of mass. All right? Now you can imagine one single atom is very, very small and hard to actually take the mass of, right? It's very hard in terms of actual grams, right? we saw a while back that a proton was a very, very small number, its mass. And so if you just have 6 of those and 6 neutrons, then the mass is going to be extremely small. So we needed to do something so that we could use this mass and these numbers on the periodic table and perform chemistry in the lab, for example. Okay? So we initially just think of the mass as in units, right? But we had to introduce something that's called the mole. The mole. Now, that's what we call it today, the mole. But in a long time ago, it was initially called the mole because it was an abbreviation for a molecular unit. A molecular unit. They used to think that everything was molecular. They didn't know that some things were ionic in nature. And so they thought that everything, they knew that ionic compounds existed, but they thought that they were molecular in nature in terms of how they went around in their space. And so they used to call an amount of a material a molecular unit, which was shortened to a mole. A mole. So if I say I have a mole of something, it's saying that I have 1 molecular unit or 1 amount. And this number is the number that we chose to be that amount. Okay? We chose this number, so don't get confused into thinking it's really a terribly magic number. There's a reason why we chose it. We chose it because if you take 12 grams of carbon-12, this is how many atoms of carbon-12 you get. All right? But you can gradually think about that, and that will kind of settle on you. If you don't quite understand what that means, that's okay. But the only thing that we have to kind of remember is that the mole is a number. And there's other numbers that have names, right? There's a dozen. Have you ever heard of a dozen?
Yeah.
How many is a dozen?
12.
12. A dozen is 12. If we grew up thinking, oh, a dozen, that's 6.0223 times 10 to the 23rd. We go, oh, okay, that's fine. That's what a dozen is. And if somebody said, a couple, I have a couple of cats. What does that mean? What's a couple?
2. 2.
2? Yeah, a couple is 2. Okay? And there are a few other names or numbers that have names, right? And a mole is just one of those numbers that gets a name. It gets a name. Okay? And its number for the mole is 6.0223 times 10 to the 23rd. So, if I have a dozen donuts, how many donuts do I have?
12.
If I have a baker's dozen, have you ever heard of a baker's dozen?
Yes.
You have heard of a baker's dozen? The baker always makes 1 extra for himself. So if I have a baker's dozen of donuts, how many do I have?
13.
13, that's right. Now, if I have a mole of donuts, how many donuts do I have?
6.0223 times 10 to the 23rd.
That's right, that's right. Is that a lot of donuts? What's that? Say it louder into the microphone.
Isn't that a lot of donuts?
Oh, that's so many donuts. That's so many donuts that if you actually had that many donuts on the Earth's size would have to be larger than our whole solar system type thing, right? We'd reach out to the sun with so much space that those donuts would take up. A lot of space, right? I can't remember exactly, but if you had a stack of papers and each stack was stacked on top of itself and there was 1 mole of paper, it would go all the way to the sun and back several times, right? So this is a huge, huge, huge number, right? That means times 10 to the 23rd. That means you have to take that 6 and move it over 23 times. Okay? So, you know, we don't have this much of everyday common stuff around. But if you get really small, then yeah, we do. We do have 6.02 times 10 to the 23rd atoms of water in us, right? Yeah, that's for sure. Sorry, molecules of water or atoms of oxygen, atoms of hydrogen, carbon, right? Yeah, definitely. Definitely have that many. Way more, in fact. Okay? So, it's a really big number for something like dogs. Yeah. If there was that many dogs on the earth, there wouldn't be any room for humans, right? So, this is a big number, but for small things, it's the kind of number we need to be able to count atoms and count molecules. Because you don't need to just talk about a mole of atoms. You can talk about a mole of molecules. You can talk about a mole of ions. You can talk about a mole of ionic units, right? You can talk about a mole of, what else have we mentioned? Molecules, atoms, ions, compounds. You know, you can talk about a mole of anything. And the thing you really want to remember is that that number, 6.0223 times 10 to the 23rd, is what a mole is. All right? But usually what we do is we talk about the relationships between the number of moles of one atom to the moles of another atom. Okay, and we'll use that for some examples. Here in this picture, this is a mole of sulfur. So it's not, you know, enormous. This is a mole of copper. Here's a mole of mercury. Okay. Here's a mole of iron. A mole of carbon. All right. And notice, see, 1 mole of carbon is 12 grams of carbon. And if we bring up our periodic table, where's the periodic table? There it is. If we bring up our periodic table and look at the mass of carbon on the periodic table, it says 12. So we're saying 1 mole of carbon is 12 grams of carbon. If we look at iron, 1 mole of iron, 55.8 grams of iron, 55.8, right? So let's do that again for sulfur. 1 mole of sulfur atoms, 32.1 grams of sulfur. And there it is right there, 32.066. Okay? So what we're learning is that this number right there, see that number for phosphorus or for arsenic or for germanium, silicon? Those numbers are how many grams you have to have if you want to have 1 mole of the material. All right? So if I have 12 grams of carbon, I have 1 mole of carbon, or I have 6.02 times 10 to the 23rd atoms of carbon. Okay?
Doesn't that mean carbon is really, really small?
Oh yeah, it's really, really small. All of these atoms are extremely small, right? And we can think of it this way as well. Here's helium, 4 grams to get a mole of it. Here's carbon, 12 grams to get a mole of it. We can see 4 and 12, carbon is 3 times more massive than helium. Or in other words, you need 3 times as much mass of carbon to get the same number of carbon atoms as helium atoms. All right? So the relationships between, for example, neon and argon, argon is twice as heavy as neon. Right?
Wait, doesn't that mean hydrogen is the smallest thing on here?
That's right. That's right. Very good. And you know, we really have that set to 1. 1. It's the smallest thing, the lightest atom, and everything is in units of relative to this hydrogen being 1, because we found that this was the smallest, so we gave it a number of 1. That's what we did initially, and later we changed it so that we could do the experiment a little bit better. We changed it to carbon, but it worked out really well in that the mass of 12 grams of carbon-12 was 12. So we were pretty fortunate that way. Okay? So this is good. This is good. It's a unit.
Pause?
Yeah. All right. So why is a mole 6.02 times 10 to the 23? Because that's what we found. That's the number of carbon atoms we found were in an actual 12-gram sample of carbon. So we set that as our number for a mole. So what does that mean? Well, that means that if we look at any square on the periodic table, any rectangle, the number on the bottom, the mass number, is how many grams you need to weigh out if you want to get 1 mole of that material. So why is this cool? Why do we care? Well, a lot of times this is on the side of the bottle. So if I went to the chemistry lab and I said, hey, do you have any carbon? And they gave me a container of carbon on the side, it would tell me the mass necessary to get 1 mole of carbon. It might say FW for formula weight, or AW for atomic weight, or MW for either molar weight or molecular weight, or it might say MM for molar mass or molecular mass. All right, there's lots of ways that you'll see on the side of the bottle. But what they were telling you is how many grams you need to weigh out to get what?
1 carbon.
How many grams? This is how many grams of carbon you need to weigh out if you want to have 1 what?
1 mole.
1 mole. That's right, 1 mole. Okay. Now, don't be afraid of the word mole. It's just the chemist's version of the unit that we use to cook with. For example, sometimes recipes use tablespoons. All right. We use a mole. Sometimes recipes use cups, but chemists use moles. Those are our units. Okay? So, let's say I have some chemistry that I want to perform. I want to combine some carbon with some oxygen to make carbon dioxide. And I want to control exactly how much carbon dioxide I make. I want to see which plants best absorb carbon dioxide out of the atmosphere so that I can help the world, right? But I can't tell how much is absorbed if I don't know how much I start with, right? So I'm going to create some carbon dioxide by burning a precise amount of carbon in some oxygen to form carbon dioxide, but I want to know exactly how much carbon dioxide I have. Well, what's great is I can use the number on the side of the bottle of carbon that I have. I can weigh it out. I can use the oxygen from the air, right? And I can know exactly how much carbon dioxide I'm going to have. So, for example, all right, how many grams of carbon do I need to weigh out if I want 1 mole of carbon? 12. That's right. Speak it to the microphone. 12 grams of carbon are what I need to weigh out to get 1 mole of carbon. Now, the oxygen gas, O2, there's 2 oxygen atoms. Do you know how many grams are in 1 mole of oxygen?
15.
Look again. What's it say?
16.
16. That's right. 15.9999. Essentially 16. So if I need 2 atoms of oxygen, how many grams do I want it weigh out?
32.
32, very good. 32 grams of oxygen. And then when I'm done, if I combine my 12 grams of carbon with 32 grams of oxygen, I know how many grams of carbon dioxide I'm going to get. How many am I going to get?
44.
Very good. 44 grams. Now, we knew that from the law of conservation of mass, but we can also know that by seeing that this equation up here is telling me 1 mole of carbon combined with 1 mole of oxygen gas yields 1 mole of carbon dioxide. I don't have the ones in there, and we don't show the ones, but they're there. One, and you could say 1 atom of carbon with 1 molecule of oxygen yields 1 molecule of carbon dioxide. But we can also say 1 mole of carbon reacts with 1 mole of oxygen gas and yields 1 molecule of carbon dioxide. And I can know the mass of that molecule of carbon dioxide simply by counting up the atoms. There's 1 carbon and 2 oxygens, right? 1 carbon, that's 14. 2 oxygens, that's 2 times the 16, right? And if I add that together, add that all together, I get, that's 44, right? So there's 44, you need 44 grams of carbon dioxide to get 1 mole of carbon dioxide, right? Like I said, you can have moles of atoms, you can have moles of molecules, molecules of elements, but also molecules of compounds. So to find how many grams you have to have of a certain material, you just add up the masses for all the elements in that compound, in the compound's formula. Okay? So, we have what are called, again, atomic masses. That's the mass of given atoms, just any old atoms, like on the periodic table, right? The atomic mass of aluminum, 26.98. The atomic mass of nitrogen, 14.0. The atomic mass of fluorine, 18.99, right? So those are the masses necessary to have a mole of that kind of atom. We can also have masses necessary for molecules. Molecules. What is the atomic mass of water? You have any ideas? What is, not the atomic mass, it would be called the molecular mass because it's not an atom, it's a molecule. What's the molecular mass of water? How would we determine that? 2 for the what?
Hydrogen.
Yeah, there's 2 hydrogen. Each hydrogen is 1. And then there's
Yeah, so 2.
2. But then the oxygen is how much?
16.
16.
16 plus 2 is 18.
Very good. What is the molecular mass of water? It's 18. And what are the units? 18 what?
Moles.
No, 18 grams.
Grams.
And 18 grams is equal to 1 mole. Oh, looky there. I feel a conversion factor coming on, right? 1 mole of water is equal to 18 grams of water. Or I could say 18 grams of water is equal to 1 mole of water, right? Those are our conversion factors that we can make from the molar mass of water. Very good. Ionic compounds aren't molecular, so we wouldn't call them the molecular mass, but we would call it the formula mass. Formula mass you can use for any compound, right? Because it's the formula, right? So can you tell me what's the formula mass for sodium chloride. What's the formula mass? How many grams do you need to weigh out to get a mole of sodium chloride? Here's where the calculator comes in handy, right? What numbers am I going to put in my calculator?
Is 35.
35 plus
23.
23. Very good. So 58. Now, we do have to pay attention to the chlorine here. It's 35.45, right? Sodium is pretty much close to 23. So it's really about 58.45. So 58.45. And what are the units?
Grams.
Grams for every what?
1 mole.
Yeah, for every 1 mole of sodium chloride. Okay, very good. So here it is. What's the formula mass of, what's the name of this compound?
Yeah. Where's the Helium?
It's what you do to a dead chemist. What do you do to him?
Barium.
Yeah, good job. You bury him. Barium, and then what's the rest of it?
Phosphate.
Phosphate. Very good. Barium phosphate. Do I have to call this compound barium 2-phosphate?
No.
No, because it's from the representative elements here. Excellent. Okay, so what numbers do I have to add together to know the formula mass of barium phosphate? Look down here. They gave us some atomic masses of the different elements. Isn't that nice?
Oh, for BA137, so 137 plus 30.
We can just round up. 31.
31.
What's that?
Yeah, 31.
31.
31.
Okay.
32. No, wait. 64.
64. How'd you get 64?
16 times 4.
16 times 4?
Yeah.
Because there was 4 oxygen? Is that what you're saying?
Yeah.
Well, how many bariums are there altogether?
Oh, 3.
There's 3 bariums, huh? Is there just 1 phosphorus?
Yes.
Look close.
Oh no, there's 2.
There's 2 phosphorus. Good job. And really, how many oxygens are there?
So 100.
Wait, how many oxygens are there?
8.
8 oxygens. Okay, that's a lot of math to do, right? Two, 3, 4, 5, 6, 7, 8. What'd you get?
601.
601. Very good. 601.9 if we would have added up all those decimal places. So, good. Very good. All right. So you see that to make sure we add up the appropriate molar mass, we need to be sure that we can determine how many of each element there are. And we've had lots of practice, so we're good at that. All right, what's the molar mass of this compound? What's the name of this compound? Can you tell me?
One second. Ammonium.
Ammonium, good.
Carbonate.
Very good. Ammonium carbonate. Those are both polyatomic ions, huh? But even though there's no metal in that compound, how do we know it's an ionic compound?
It has
It's made of what?
more than one
It's made of ions. It's made of ions, right? That's what the definition of an ionic compound is. Well, how many nitrogens do we have in that mess?
nitrogen. 8.
8 nitrogens or 8 hydrogens?
2 nitrogen.
All right, so 2 nitrogens. Each nitrogen, how much is the mass of nitrogen?
14.
Okay. How many hydrogens?
8.
8. And hydrogen's the easy one. It's just 1. How many carbons?
0.
Carbons, what's that?
Oh, 12.
Well, 12 is the mass of carbon, but how many do we have of them?
1.
1. 1 carbon. How about oxygens?
3.
3. And what's the mass of the oxygen?
16.
16. All right, we got to add that all together. Did you get it?
$96.
96. Very good. 96 grams per mole. Fabulous. So, all of our efforts to determine how many atoms there are in a compound are paying off, because now, if I want to have a chemical reaction with barium phosphate and combine it with ammonium carbonate, and I want to have 1 mole of barium phosphate combining with 1 mole of ammonium carbonate, then I'm going to need to, I know now how many grams of each I'd have to combine together to get the reaction to proceed that way. Now, you don't have to weigh out a whole mole. You could weigh out 1/10 of a mole or 1/100th of a mole, and then you could weigh out 1/10 of a mole or 100th of a mole of the other material, right? But now we know how to find out how much 1 mole actually needs to be, how much has to actually weighed out to get 1 mole of the material. Okay, very, very good work today. We'll see you later.